Great. Okay. Hello, everyone, and welcome to the MIT IoT Seminar Series. It is my great pleasure today to introduce Professor Haitham Hassanieh from the University of Illinois and Urbana-Champaign. Professor Hassanieh is an assistant professor in electrical and computer engineering and the Department of Computer Science at UIUC, where he co-leads the Synerg group. He works broadly in wireless networks and mobile systems and algorithms, and he's done a fantastic set of research and publications that have had a lot of impact. His work has won multiple Best Paper Awards, including the SIGCOMM Best Paper Award, the Mobisys Best Paper Award. He graduated, he got his master's and PhD from MIT, where he got the Sporls Award for Best Dissertation in Computer Science. And his research has also had a lot of gained a broader attention. It was selected as Technology Review's top 10 breakthroughs in 2012, if I'm correct. And he's won various early career awards, including the NSF Career, the Alfred Sloan Foundation Award, as well as the ACM Doctoral Dissertation Award, which recognizes the top dissertation in the world in computer science every year. And so with this, it's a pleasure and honor to introduce you, Haitham, today. Thank you for joining us, and very much excited about your talk.
Thank you, Fadel. Thank you all for joining us this afternoon to listen to my talk. My talk will be on millimeter wave from 5G networking to imaging autonomous cars. So millimeter wave is a high frequency spectrum. So typically today, everything above 24 gigahertz is being referred to as millimeter wave. And you can see there's a huge amount of spectrum in the millimeter wave bands. And if you compare it to today's cellular and Wi-Fi networks, where we've been operating is here. So for the past 50 years, we've been operating below 6 gigahertz, and millimeter wave has a huge amount of spectrum. And so the demand for higher data rates and more connectivity has drove FCC to open these bands, some for licensed use, others for unlicensed use. And so with this, we now have a huge amount of spectrum, more than anything we've ever had before in the millimeter wave bands. And this has two implications. From a networking perspective, this means that now we can have millimeter wave links, or the wireless links that can support data rates that are multi-gigabits per second, which is something we've never had before, like fiber speeds in the air. And from a sensing and kind of imaging perspective, the huge bandwidth allows us to very accurately kind of sense and measure time of flight, do localization and imaging. And I'm going to talk about this later in the talk. And so this talk is centered about how we harness these benefits of millimeter wave in next generation wireless networks and sensing systems to advance kind of state of the art. And I'm going to start with the networking side, and let's talk about millimeter wave networks. So there's plenty of applications in millimeter wave. So 5G, of course, is kind of the #1 application. Millimeter wave plays a central role in 5G networks, and it's going to play a central role in 6G and next generation networks because it offers a huge amount of spectrum that allows us to scale the data rates and the throughput with the user demands. But 5G is not just the only application. Virtual reality is another very important application. Typically, we think of VR as gaming, but gaming is not the only use case. Training, education, doctors, there's a lot of use cases in VR. And today, if you've tried any VR system, you're gonna have like an HDMI cable connected to the back of your head. It's very restrictive. It does not allow mobility. You have to stand in one place. And so it really does not give a good experience. With millimeter wave, now that we have wireless links that are multi-gigabits per second, you can support VR over wireless. There are also applications of connected vehicles where vehicles have to share a huge amount of sensory information, robotic networks for factory automation, Wi-Fi networks at 60 gigahertz millimeter wave, and as well as people have shown applications in wireless data centers. So this is great, huge opportunities for advancing kind of new applications and emerging applications and delivering the data rates we want, but nothing comes for free, right? So there's a catch, and the catch is as we go to high frequencies tend to suffer from attenuation, which means that the higher in the spectrum we go, the faster the signal attenuates and the lower the range that the signal can achieve. Luckily, however, millimeter wave can use phased arrays, or what we call phased antenna arrays, to focus the power. So as opposed the power goes in all directions, you can focus the power in one direction and compensate for the loss that you get from attenuation. And because we're at such high frequencies, the wavelength is so small that people are able to build very large phased arrays, so hundreds to 200 element phased array. And this means that we can create very narrow, very directional beams that kind of really improve our gain, improve our range, and kind of allow us to communicate at these very high data rates. However, this really changes the way we should think of wireless networks. So far, our wireless networks have been broadcast, which means that whenever I transmit or an access point transmit, the signal goes in all directions. No matter where my phone is, where my laptop is, it's going to receive the signal. Maybe the quality of the signal is not going to be the same based where I'm sitting, but I'll always hear the access point. Now consider what happens in millimeter wave when we have very directional, very narrow beams. This means that I have to be within the beam to be able to receive the signal. And this gets even more complicated when both kind of wireless radios are directional. Now, as soon as I move, kind of the link is broken. And I have to realign the beams to be able to communicate at the high data rates that millimeter wave gives me. This is known as the problem of beam alignment in millimeter wave networks. And it's a very important problem because unless you align the beam, unless you keep tracking and realigning, you would not be able to maintain the multi-gigabit per second data rates that we're talking about. And so the first question I'm going to ask in this talk is how can we quickly find the best beam alignment? And in this case, I'm interested in pushing the boundaries of this problem. In particular, we're interested in something called analog beamforming. Now, if you don't know what that is, don't worry. All it means is that all these antennas, these 200 antennas, they're all connected to one receiver. So I cannot sample each antenna individually, but that's what we call digital. But rather, I have one receiver that gets the sum from all the antennas. I'm interested in very large number of antennas. How far can we push this? And I'm interested in minimizing the number of measurements that would allow me to do this, to find the right alignment as quickly as possible. And to this end, I'm going to present a system called Agile Link that's able to find the best beam alignment in a sublinear number of measurements. And I'm going to tell you what I mean by sublinear in the next few slides. But before I do that, let me tell you how is this done today, right? We already know that 5G is deployed. There's already millimeter wave Wi-Fi systems. how do they do the beam alignment? The idea, what's being done today in 5G and 802.11ad, which is kind of the millimeter wave Wi-Fi standard, is that first the client kind of creates what we call a quasi-omnidirectional beam. So it kind of creates a beam that not perfectly omnidirectional, but it's kind of almost omnidirectional. And then the AP scans. So the AP tries all different directions until it finds the one that it can reach the client on. And then it repeats the process from the client side, where the client scans and the AP listens on all directions at once. And now if there's n possible directions, this means that there are n, I need at least order n measurements to be able to figure out the right direction. Now, the reason we're concerned with kind of this linear time is that every measurement means that the AP has to transmit a packet. The AP has to transmit a packet saying, I am AP1 with this is my IP address, this is my MAC address, and I am transmitting this packet along sector 60 degrees. And then it moves and transmits another packet saying, I am AP1, I'm transmitting this packet at 65 degrees. I'm transmitting at 60. So every measurement is a packet. And so it kind of becomes very important to reduce the number of measurements. And there's a lot of research and even empirical research from University of Minnesota where they measured kind of millimeter wave 5G deployments and find that it's very susceptible to mobility. Clear, as you keep moving, the link keeps getting disconnected. And so it's very important to do the scan faster. And so what we would like to do is to find the right alignment in a sublinear number of measurements. So I don't want to go and scan and try every single direction, but rather I want to be able to do it in a sublinear number. So how are we going to do that? In order to do that, we are going to leverage the sparsity in the millimeter wave channel. Now, let me tell you what I mean by that. Typically, basically, people have found that millimeter wave channels are sparse, which means if you have one transmitter and one receiver or two radios, there's only a few paths that the signal can travel between the transmitter and the receiver. Basically, because we kind of have directional communication and because at millimeter wave frequencies, signals do not scatter as much as they do at kind of Wi-Fi 2.4 gigahertz or kind of today's cellular and Wi-Fi frequencies, you get more of reflections. And as a result, basically, you get kind of a sparse channel. And people have done a lot of measurements indoor and outdoor that show at most you get 3 to 4 in the at most number of paths where you can align the beam. And so this AP can choose to align its beam along the direct path, or if that path is blocked, it can choose to align the beam over kind of a reflected path. And so what the goal, our goal is to discover these two paths, to say that I can align here or here, and then pick the higher SNR one. So how are we going to do this? How are we going to leverage the sparsity in the millimeter wave channel? To do that, let me first tell you how the phased array, the antenna array on a millimeter wave as a kind of radio works. So basically, what you have here is an array of antennas. Each antenna is connected to something we call a phase shifter. And so what a phase shifter does, it takes the signal and it rotates the phase, the complex phase of the wireless signals. So you can think of it as if it multiplied by a weight, A, but this weight is some complex number, e to the j phi. And so what we do is we typically set the phase on each antenna, and then we get the sum. And the sum is one measurement that we can take. And so I want you now to think of phased arrays as a Fourier transform. I'm not going to have the time to derive this, but if you take a look at the phased array equation and the Fourier transform equation, you're going to find that they're very similar. In fact, basically, in the phased array equation, we can look at the power from a certain direction or focus the beam in a certain direction by multiplying by changing the phase on each antenna by e to the j2 pi cosine theta. And so if you do a change of variable from cosine theta to f and from antenna number to t, you'll find that it's exactly the same. So now we can think of an antenna array or phased array as a Fourier transform. In a Fourier transform, we have time samples. We take the FFT or DFT and we get frequencies. In a phased array, we have antennas or signals on the antennas. We take the FFT, we get spatial directions of where the signal could have come from. So now we can model the problem mathematically. And so if we have basically the signal on each antenna or the channel on each antenna, I'm going to call it H, a vector H representing the channel on each antenna. This vector is nothing but the inverse Fourier matrix times a vector X, which represents the direction of where the signal could come from, or the different paths where the signal could come from. And so now note that I do not have access to H, my vector H. I only have access to a sum of H after I multiply it with some weights. So my weights, these A weights, are nothing but a phase shift. So they're e to the j phi m. And so every time I want to beam in a certain direction, what I'm really doing is I'm setting these phi m's to create a beam along a certain direction. And the measurement I get is the sum of the signals on each antenna weighted with this phase shift. So I can write this as a vector A times a vector H. And remember, the vector H is the inverse Fourier matrix times the vector X. Now, this is just one measurement. So this gives me just one measurement of the channel. I can repeat this. So every time I look at a certain direction, it's another measurement. I can repeat this and collect a set of measurements, which give me a vector Y, which is a matrix A multiplied by inverse Fourier transform, multiplied by the vector X, which is now a sparse vector that I want to recover. And at this point, if you know anything about compressive sensing or sparse recovery, this should ring a bell, right? This is just a standard sparse recovery problem. I have a sparse vector X in the Fourier domain. I have a mixing matrix. I have some constraints on the matrix A, and we need to minimize the number of measurements Y to recover X. However, it's not that simple. And the reason is once we take this into a practical system, so once we go into real hardware, it turns out that basically there's something called carrier frequency offset. Now, if you don't know what that means, don't worry. What that means is the transmitter and the receiver are not synchronized in frequency. And then what that does is it takes the phase of the signal and multiplies it with some random number. That's all you need to know about this, okay? So if you know what carrier frequency offset is, great. If you don't know what it is, it's just some hardware frequency offset that creates a random phase every time I take a measurement. And this random phase, I don't know it, and it completely corrupts my signal. And so the phase of this measurement is meaningless. So I only can look at the amplitude of the measurements. So I now have only access to the amplitude of the measurements, and I need to recover the vector x still. So how are we going to solve this? To solve this, we're going to leverage a sparse Fourier transform framework. And let me tell you at a very high level how the sparse Fourier transform framework works. So let's consider the access point, the AP, and the client. And let's say the AP is at the direction of 60 degrees relative to the client. Instead of creating kind of a beam and scanning it, what I'm going to do is create what I call a multi-armed beams. So this is a beam that have arms or kind of sub-beams in different directions. So I can try this, and this will tell me, well, the client is likely going to be in one of 4 directions. And now I can try a different kind of multi-arm beam, and it's going to give me a different set of directions. And I can intersect them to find that, oh, the client is at 60 degrees. Now, of course, this is a very kind of simple example, and things are more complex. How can I choose these multi-arm beams to ensure that I get this direction? Maybe the client is at 75 degrees and none of these beams, kind of these choices have 75 in them. So what do I need to do? How do I need to design these multi-arm beams to ensure that I'm able to recover the directions where the signal could come from? To do that, the idea is what you need to think of this multi-arm beam. Think of it as a random hash function. So the multi-arm beam takes signals from different directions and gives you kind of one value, which is the power. A random hash function takes kind of different values and maps them to one bin. And so what we need to do is kind of create multi-arm beams that give us random hash functions. So they cover all directions, while at the same time they randomly map directions into bins. And so if I do that, then I can use a voting approach. After I hash these kind of directions into bins, because my signal is sparse, I can use a voting approach to solve which directions have power or which direction the signal could come from. The only thing is that these random hash functions are not perfect, right? So this multi-arm beam is not a perfectly mapping exactly every direction to a bin. There is some weighted function, and that's why we need to do what we call a soft voting as opposed to a hard voting approach to account for what we call leakage, which means that this multi-arm beams might still leak some signals from other directions outside these arms. And so this is kind of the algorithm at a very high level. Let me tell you what we can prove about this algorithm. So this slide has a lot of math, so don't worry, we're not going to go kind of into the equations, but at a very high level, what we can show is that we can recover, if we have k possible paths, if I have n directions where that I can beam to, and the signal could come from k possible path, and remember k, the system is sparse, so k is much smaller than n, then I can recover kind of these paths or directions in k log n measurements. And this takes nk log n computations. So the computations are not sublinear because I need to account for kind of this side lobe leakage and do the soft voting. But computation is not the bottleneck in this case, right? So we're not worried about computation. We're worried about measurements. And with this algorithm, you can do it in k log n. And what the theorem 1 and 2 are showing, are proving, is that you can recover the value of kind of the path or the power along that path with very high probability. So you can accurately recover its value and you can get the good estimate with very high probability. And so we tested this on real hardware. So we built our own phased arrays. So these are small, but we use them to collect a lot of measurements and a lot of traces, which we then use to evaluate the algorithm on kind of from real measurements. And so here is kind of a plot where we show the size of the antenna array on the x-axis and the reduction in the number of measurements. And in this case, we compare it to two system. One is 802.11ad, which is kind of the Wi-Fi standards for millimeter wave. This is kind of very similar to what 5G is doing. It's in fact exactly kind of the same beam alignment protocol. And then an exhaustive search which tries all possible directions from both sides. And so this is kind of a very naive algorithm. And what we see is that with this algorithm, we can get an order of magnitude fewer measurements as the number of antennas on my hardware goes up to like 256. And as I've shown you, there's already kind of devices on the market that have 256 and 384 antennas on a single device. Does this translate to real measurements? If you account for the protocol and kind of compare how long it takes to find the right alignment once you do this in the protocol, so you send the packets and you receive them, you'll find that with this algorithm, you can maintain a latency, a beam alignment latency that's less than 1 millisecond, even as the number of antennas grows to 256. Great. So now we know how to quickly align the beam if we have kind of a single user. But the directionality of millimeter wave offers another opportunity here. It's kind of both a blessing and a curse. It's a curse because now we need to align really fast, but it's also a blessing because once you have directional links, you can actually put a lot of them in the same location. Today with Wi-Fi, it doesn't make sense to add more access points, or with 4G, it doesn't make sense to add more base stations because they're gonna interfere. Whereas with millimeter wave, I can add a lot of base stations. So that's what we see with small cells in 5G, or a lot of Wi-Fi APs. And because of directionality, I get spatial reuse. And in fact, the narrower my beams, the more kind of spatial reuse I can do. And so now, how do we extend this to many access points or many links? How do I do kind of this many-to-many beam alignment? And turns out that multi-link beam alignment is challenging, which means I cannot just simply align the beam of each link independently and things will work fine. Consider this example. If both access points align their beams to their clients, their signals are going to interfere. And even worse, because they're using directional transmission and reception, they won't even hear each other, which means that carrier sense, which is the typical scheme to avoid interference in Wi-Fi, cannot be used in this case. And there's lots of literature on this. Basically, they won't hear if access point 1 listens, it will say, no one is transmitting, I can transmit, right? Now you could say, well, I can coordinate these access points. I can tell them, do not transmit in the same direction. But that's not sufficient. Even if the access points are transmitting in completely different directions, there's a lot of multipath, both indoor and outdoor. The signal could bounce off some wall or some reflector and come back and create interference. And so we cannot simply align the beams of each client and AP independently in such cases. And so the second question I'm going to ask in this talk, how do we scale kind of these millimeter wave networks to many links and do kind of align their beams while maintaining this multi-gigabit throughput per user? So I don't want to divide the channel. I want them to transmit and receive at the same time. And I'm going to present a many-to-many beam a system called BounceNets, which is a many-to-many beam alignment protocol that can enable many links to operate at the same time without interfering. And so at a high level, this protocol leverages the same thing that we've leveraged in the first protocol, which is that the channel is sparse, which means that this AP has only two choices to align its beam. It can send its signal over the direct path, or it can send its signal over the indirect path. Now, I want you to think of this as routing, right? This should remind you of routing. In routing, we say, what path do I send my packets? Here, we're looking at physical signal. So it's physical signal routing. And so now, instead of routing, in this case, instead of both APs routing their physical signals along the direct paths, we can have one AP, in which case they will collide and interfere. We can have one AP route along the direct path and another AP route along the indirect path or the reflected path. And in this case, they can both transmit at the same time, and we can increase the network throughput. And you could do this on the reverse link as well, on the uplink as well. And so with physical signal routing, we can enable more efficient beam alignment because we can ensure that, okay, I choose the routes that do not kind of match or do not collide. Now, of course, this seems a bit unfair, right? Because one client is communicating over a direct path, which has a lot of SNR, and another client is communicated over a reflected path, which supposedly have lower SNR. And so simply doing this makes it unfair to some clients. And so to address this, what we need to do is, instead of creating one many-to-many alignments, we need to create multiple of these many-to-many alignments. And then each time we do that, we need to maximize the number of nodes that can transmit at the same time, while we ensure that every time the client gets a fair share to transmit at the highest data rates. So we're trying to balance two things: maximize the number of links that can transmit and ensure fairness among clients. Now, I'm not going to have time to go into the details, and I encourage you to read the paper, but at the high level, what you need to do is decouple routing along direct links or direct paths or line of sight path from routing along non-line of sight paths. And so once you separate these two problems, the problem becomes tractable, and you can kind of ensure that every time you pick an alignment, you kind of are fair to some of the clients. So as I said, I'm not going to have time to go into the details, but let me show you what this can give you. So this is from a real experiments back in our basement lab at UIUC, where we had 10 access points on the wall and 10 clients in kind of a room. And the thing in gray are kind of metal cabinets. So metal cabinets tend to reflect much stronger than walls. So we kind of are highlighting them here. And so the first step was to kind of expand the beam search algorithm to find kind of all the paths between any client and any access points. And in the paper, we highlight how to do this very efficiently without adding a lot of overhead, because discovering all these paths, right, can take a lot of time. So how do we amortize the cost? But once we do that, now we can figure out which paths are going to interfere and which paths can be kind of routed on at the same time. So if we route on these paths at the same time, we kind of don't get interference. And so here's one kind of run of the algorithm, the protocol. And so in the protocol, in the first time slot, it chose to kind of chose this alignment. So in this case, 9 of the 10 access clients were able to transmit and receive. So this is two-way communication at any point in time. So they have to be able to do it both on uplink and downlink. And so both on uplink and downlink, they're able to transmit and receive at the same time without interfering. As you can see, some of them are on a kind of reflected links. One of them did not get a chance to transmit. And so kind of we change the alignment in the next time slot. And so on until everyone gets kind of a fair share. And so we've evaluated this mainly indoors, but you could imagine that you could extend it outdoors to cellular base stations where kind of if your line of sight is blocked by a building, you route your signal over a reflected path and so on. And we've tested it using different hardware, both phased arrays as well as horn antennas or directional millimeter wave antennas. And here are some of the results. In the top graphs, you see the total network throughput versus the number of clients. On the left, you see for a phased array. On the right, you see for a horn antenna. And you can see basically the red curve is kind of bounce net. And you can see that you can get significant improvement, like 6 to 7 times higher network throughput and spatial reuse compared to kind of the standards or kind of a straightforward baseline. But more importantly, if you look at the worst case client, which means as opposed to looking at the average, how much the average improved, look at how much the 90th percentile improved or the worst case client improved, we see that basically, especially when the beams are not super narrow, like 3 degree, when the beams are like 12 degree or you're using phased array, basically you get a major improvement in the worst case client. So the average might not be as big, but the worst case client can improve its throughput by 7 to 13 times. Great. So this is kind of what I want to say about networking. And in the remaining time, I want to talk a bit about millimeter wave sensing. And specifically, I'm going to talk about millimeter wave sensing in the context of self-driving cars. So there's a lot of interest in kind of autonomous driving, and we've seen more and more companies investing a lot of money in basically achieving what we call level 5 autonomy. And what level 5 autonomy means is that the cars can drive on their own anytime in any weather. But at the same time, we're seeing that basically there's a lot of problems for self-driving cars, especially in bad weather and fog. And this is mainly because they rely on optical sensors. So cars like Tesla rely on vision cameras, and cars like kind of the Facebook would rely on LiDAR. And both are optical sensors. They don't function well in fog and bad weather. And so here's an example from a Tesla drive. So this one is in clear condition, and we've highlighted kind of the dashboard on the left. And you can see as kind of the driver drives, you can see on the left that it can detect the cars passing by. And basically everything works just fine. Now, the same car in kind of very foggy environment, you can see that it starts to abort self-driving. It starts to tell the driver kind of you drive, and you can see that it starts to miss the cars passing by. So it does not see, the sensors do not detect the cars that are passing by in dense fog. Millimeter wave, on the other hand, millimeter wave radars can function in kind of fog, sandstorms, blizzards, and low light conditions. So they don't have a problem in these scenarios. And so The question is, can we use millimeter wave radars for imaging in scenarios where kind of LiDAR and cameras fail? Now, we're not proposing to completely replace kind of cameras and LiDAR, but rather to augment them with millimeter wave radars. So today, the state of the art in kind of automotive radar is that it's used mainly for 1D ranging. Basically, it's on not just self-driving cars, even Toyotas, Hondas have them. Basically, it tells you how far the car in front of you is and how much speed. And there is work to expand this to 2D ranging. But our goal is to get a lot more sensory information. And what we would like to do is to get a 3D imaging, not just ranging, not just tell you there's something there, but I want to show you what is there. And to do that, to go from 2D to 3D, we need 2D phased arrays. Now, luckily, 5G has actually pushed research into delivering large 2D millimeter wave phased arrays. And these are the same ones I showed you earlier, kind of these massive phased arrays with many, many antennas, these 2D phased arrays that allow us to kind of steer the beam in 3D and get kind of capture the signal in different regions in space. So you combine this with the very large bandwidth, which would give you very accurate time of flight measurements to the car, and you can get 3D imaging. Unfortunately, the 3D images you get are nowhere near what we would like to get. So here's an example of a 3D image of this car or 3D heat map that you would get from LiDAR. So this is the 3D point cloud on the top right. And on the bottom, I'm showing the 2D projection, 2D projections. Now, if I don't tell you that this is a car, you might not even know it. The resolution is so low, you only see blobs. And as I said, if I don't tell you it's a car, you might not realize it's a car. If I overlay the silhouette of a car, you start to realize, well, okay, this is what these reflections mean. This is what they correspond to. But as you can see, the resolution is so low. Not only that, the system suffers from specularity, which means that some of the reflections that you send to the car do not even come back. And there is multipath that creates artifacts. So how are we going to deal with that? So today, 3D millimeter wave imaging is done. You probably have seen it. And basically, the way they do it is by limiting it to very close range. So if you put the radar very near to the device, then you're good, right? Because even if your beam is not super narrow, kind of at very near distances, your resolution is still high. And you've probably seen, as I mentioned, you've probably seen this in airport scanners, right? In airport scanners, to get a good image, they have to put you with a human-sized array. The array rotates around you to make sure it captures measurements from all different directions, and it's very close to you so that the resolution is high. And there's been attempts in research to kind of use deep learning to improve the resolution, but we're still far from what we would like to achieve. The results are still nowhere near as good as kind of being able to tell what is being imaged. And so in the last part of this talk, I'm gonna tell you about how we can do high resolution 3D millimeter wave imaging using 2D phased arrays. And I'm gonna present a system called Hawkeye that can give you high resolution through fog, there's a typo here, through fog 3D imaging. So the idea is as opposed to just use a convolutional neural networks, what we do is use conditional GANs, basically. And the idea is basically there are problems here that simply cannot be solved with signal processing. like specularity and the low resolution. And so taking a data-driven approach could help us recover the high-frequency shapes in details. And the reason we believe this is doable is that there's a particular geometry of the image, of the kind of stuff that we're imaging. It's not completely random, right? When I am driving a car, I'm unlikely kind of to see an elephant unless I'm maybe in some parts of the world, right? But basically, the stuff that appears on the road, I'm not going to see a couch in the middle of the street, right? So it has a certain structure, and we can leverage that. And GANs have been proven very effective at problems like super resolution, learning image prior, image transformation, etc. However, the problem is that GANs have mostly been optimized, customized, and trained for vision. They're basically for cameras. And when we go to radar, we have what we call a dimension and perceptual mismatch between the 3D radar images and the 2D cameras, which would give us the ground truth for training. Also, radars have high resolution in terms of depth because the bandwidth is so high, we have this kind of high resolution information. We don't want to lose this information, which might not be there in the 2D depth cameras. And finally, there's not enough training data for radar. For images, you get thousands, tens of thousands, hundreds of thousands of images that you can train on. For radars, there's not even a data set for 3D radar out there that you can use. So to address these problems, what we do is we customize the GAN to be able to take as input 3D mmWave heat maps and convert them to 2D stereo camera or depth maps, which we then train using a stereo camera. And then we use skip connections in our network to preserve the high resolution depth information that radar gives us. And we modify the loss function because if you know anything about GANs, you know that GANs are optimized for realism, like they're used in deepfakes. So we kind of modify the loss functions to ensure accuracy, like we add L1 loss, a perceptual loss, and geometric prior loss. For the training data, we build our own data collection platform, but even that takes a lot of time. So we built a simulator. So we built a data simulator that takes CAD models and simulates how kind of the radar reflections are going to look like and what's the radar 3D heat maps. And in fact, this is what we train our system on. We train our system on mainly simulated data, and then we test it using real data. And so let me show you some of the results really quickly. So here's the scene we're imaging on the left and the ground truth from the stereo cameras. We use a fog machine to simulate dense fog, in which case we don't get anything from the camera. And this is the radar, low resolution radar heat map. We take this and pass it through our GAN, and this is the image that we recover. And you can see kind of it recovered the high frequency information from the that's available in the ground truth. It actually filled in the missing parts due to specularity, and it rejected the artifacts that were created by multipath. Now here's some more kind of results, and you can see that kind of it can recover the shape, the direction, the orientation. Now there's a lot more results on the project websites and there's also quantitative results to measure kind of the distance of the car, the orientation of the car, and so on. But it's important to mention that this has mainly been trained with simulated data. And so these have never been seen in kind of during training. It also can work for multiple cars, but still not as robust. And so all the data set we made available on the project website, as well as the code for the simulator that can generate a lot of data for you to train on, it's all made available and open sourced. Great. So this kind of, we've come to the end. I've presented kind of two parts, one in millimeter wave networking, how we can push the boundaries to get very fast beam training, to get very extensive dense spatial reuse, and then how we can push the boundaries in terms of imaging to get high resolution and millimeter wave imaging. And moving forward, of course, this is just a first step. As you can see here, we can only do cars. Ideally, you would like to kind of image humans, bicyclists, get a complete 3D image of the car. And at the same time, there was recently a 6G kind of summit, and the view for next generation wireless networks is it's going to blend communication and networking with sensing. So next generation wireless networks not only is going to send data, but it's going to sense while through the signals. And so how can we combine these two parts to give a more holistic systems that can both sense and do networking? Now, this is only a part of the research that my group does. And in the last minute, I'm just going to give you an overview of some of the ways that we've been working on to push next generation wireless networks. Another thing in terms of millimeter wave that we've been working on is millimeter wave wireless networks on chip. So for multi-core processors, wired networks are becoming a bottleneck, which means they're not as fast enough to transfer the packets between cores as kind of the cores are able to do computation. And there's kind of wireless networks can significantly improve kind of the network because it's broadcast and because it's single hop. However, there are problems when it comes to traffic patterns and designing the protocols for wireless networks on chip. And what we've done is leverage deep reinforcement learning to learn new protocols as opposed to hand-tuned protocols, which are kind of very hard to figure out. We also kind of design cheap, very low power kind of sensors that can sense multiple gigahertz of spectrum in real time using kind of MEMS acoustic resonators. We've also shown how to detect, sense what type of liquid is in a bottle without opening the bottle using just wireless signals that pass through it. We also work with Facebook to kind of build wireless mesh networks to deliver connectivity to remote and poorly connected areas. And recently, we've extended our work to push next generation wireless networks to in-body micro and nano implants using a new mode of communications called biomolecular communication. So I encourage you to check all this stuff out. I need to acknowledge my group and my students. They are the ones who kind of do all this amazing work. Thank you very much for listening. I'm happy to take questions. Thank you all. And that concludes my talk. Thank you.
Great. Thank you very much, Haitham, for a fantastic talk and for all the exciting work that you've told us on millimeter waves from 5G to self-driving cars, as well as the other work that you've been doing. We have a few questions, so we have some time for questions. Maybe we can take a couple from the crowd. Saad, would you like to go ahead? And now you can unmute yourself.
Yeah, sure. So first of all, thank you, Haitham, for giving such an exciting talk. So I actually have 3 questions. So my first question is that, so at the beginning, you said that at these high frequencies, the signal doesn't really scatter, it just reflects off different surfaces. So my question is that if there are, so like when you're doing many-to-many beam alignment, and if there are many people who are like let's say you're in an environment where you just have 3 paths to a specific client. And if there are 3 different clients who are like very near to each other so that all of them get the same path, like all of them get the same directions available to them. And now let's say if a 4th client comes there and also stands very close to them, close to those 3. So like, would this like reduce your overall, reduce the overall performance at the client's end? Like, so if there were only 3, then you can give 1 path to each of them and still be able to get like some throughput? So that's my first question. You're muted.
Okay. So of course, if the clients are kind of co-located, right? Now, the good thing is the APs are not co-located. So even if the clients are, you can make the APs very separable. But
Right.
still, you're right that the point, this is spatial reuse. So if in space, they're at the same location or very nearby location, then the spatial reuse opportunity is going to be lower. So in that sense, you're right. Kind of the assumption is that they're not all sitting next to each other. But remember that as the beams get narrower, kind of the closer the clients can be to each other, and this is something we do see in practice, right? So if you use a 3-degree versus a 12-degree beam, it means that they can come closer to each other.
Right. So my next question is that if like there are different people in a room and let's say all of them are moving, so the channel is constantly changing, like in that scenario, does the system, like is the system able to figure out the new paths in time? Or
yeah, so that is kind of the second half of the work that I didn't get to talk about, is how do you quickly kind of find for all the clients, right? So because you're not just interested in finding the direct path, you also want the indirect path, and you want the interference path. And so what you can do is design an algorithm that amortizes the cost, which means that when one guy is kind of running the beam alignment, everyone listens. And when everyone listens, they all kind of at once figure out kind of what directions they could receive signals from. It might not be my access point, but kind of I listen and say, okay, I can receive access point 2, which I'm not kind of associated with, from that direction, and so on. And so basically what we've done is design a protocol that allows you to do this within what we call a beacon interval. So the way the protocols are designed is they divide time into 100 milliseconds. And every 100 milliseconds, you do the beam alignment. So the idea is that humans move at that rate, right? So this will not work for a high-speed train, but basically we as humans don't move faster than 100 milliseconds. So the idea is every 100 millisecond, you need to track and retrain. And at the beginning of the 100 millisecond, there's kind of a beam alignment phase. And the idea is, can you figure all this out in this very short amount of time, right? Without adding a lot of overhead.
I see.
And so this is exactly the protocol design, what it does. Kind of it tries to get the minimal amount of overhead such that you don't, because you don't want to spend most of your 100 milliseconds just figuring out paths. And so that is something I didn't get a chance to talk to about, but I'm happy to describe it in more details at some later time.
Sure. So my final question is that you said like how you can get like all directions. So I don't know if this is possible, but like can't you just use, like you talked about a multi-arm beam. So just using a simple, like a single access point, and once you figure out all directions, just use a multi-arm beam at all of, like targeted at all of those directions, and like you can give all of the clients, but like I guess with this,
the clients have different data. So the clients you need to send. So basically, remember, if I have a single transmit chain, right, or transmitter, I can only send one thing, right? Even if my beam is multi-armed, I can only send. If I have multiple transmit chain, then yes, I can do that. But the idea that I want to highlight is actually it's expensive to have this kind of sort of MIMO. This would be just a MIMO transmitter, right? And MIMO transmitters are more expensive than just buying single transmitters and kind of let the protocol deal with it. So that was our approach in that paper. Instead of kind of buying a super expensive MIMO transmitter that, for example, has 10 that can support 10 clients at the same time, buy cheap, like one kind of single receiver-transmitter devices, and then let the protocol handle their ability to transmit and receive at the same time.
Right. Yeah, because this was also confusing for me because like we need multiple antennas to get one beam. So I was like, I was thinking how you're getting multiple beams, because in that figure, it like I thought that you're getting multiple beams at the same
No, it's actually, you actually divide your phased
time.
array. Not over time.
Ah,
There is more recent follow-up work, not by my group, that actually shows how to create these kind of beams by kind of really fast switching, but there are trade-offs there. So what we do is to simply divide the phased array. And in that context, because we're not transmitting data, we're just transmitting control packets, it's okay.
I see. Yeah. Thanks.
Sure.
We have time for one more question. Venkat?
Hi, thanks for the great talk. So in the millimeter imaging section, I saw in your paper that you use ray tracing for the simulation. And I mean, that makes sense because full wave simulation would be very, very expensive. So did you notice any issues because of that approximation, or did it just work?
So we have not noticed issues. So the surprising thing is that the simulator is very kind of trivial, right? So it doesn't do kind of full wave simulations. In fact, we're working now on kind of simulators that do full wave simulations, mostly because we want to image other stuff. So cars, turns out they're not very hard because mostly they have smooth long surfaces, right? And we're not trying to kind of get every single detail, right? We just want the shape, right? But as we're now moving to kind of bikes and like we cannot do this simple ray tracing over a bike because there's no like big smooth surface that you can model the reflection from. And so as we move to more complex objects, you're right that kind of the simple ray tracing does not work. But for cars, it seems to have worked fine for now.
Great. Awesome. Thank you very much. Thanks for the great talk again, Haitham. Thanks for the questions from everyone. And we'll see many of you hopefully next week again for the IoT seminar, for our next IoT seminar series talk. And with this, we're wrapping up today's seminar. Thank you, everyone. And
Thank you.
bye.